All right, welcome back. We are INFR2350 at Ontario Tech University. It's Intermediate Graphics in the winter 2021 semester, and it's week 10, part 1 of our broadcast, Water and Particles. To start us off, like I always do, let's look at where we sit. We're sitting here at week 10, and we have 2 short weeks left for the end of semester, and then, of course, our exam. Next week, what we're going to be doing is talking about exam review. Normally assignment 4 would have been due next week, but it's going to be due actually the following week. So that's going to be due on week 12, the final week of the semester, along with your GDW projects. So that's when everything is due. So, and I know there's good things and bad things about this. The good thing is that everything is due at the same time. The bad thing is that, well, everything is due at the same time. So yeah, I know it's an assignment rush week, exactly. So what are we doing today? We're doing water and particles. There's also ICE 5, which I've released. It's due Sunday. I've given you a couple days to do that extra. I know Fridays sometimes are tough to get it done, so I've given you extra time to get that done. Deferred lighting, that assignment's due on week 12, like we just said, April 11th. Next week is exam review. And again, 2 short weeks from now is your final presentation. So make sure that that'll be like our final checkpoint week, if you will, just before GavinCon. All right, so that's what's happening then. So what are we talking about today? We're talking about water and particles. Let's start off with talking about some waters. What's the best game in terms of water that you've ever seen? So here's a couple. And there's Assassin's Creed. Hopefully this is coming in okay. I'm just going to change this so you can see it a little better, optimized for a video clip. Here, it may kind of skew some things but make other things better, so I apologize for people that are watching on on Zoom, but on YouTube we might be okay. So this is pretty cool. Assassin's Creed, you can see the water effects. Like, how did they do this? How did they pull this off? Some older ones, there's Legend of Zelda, right? The Witcher 3 produced some really good water effects. I like that one a lot. GTA 5 was also kind of well known for its water. Arkham Knight, water and a lot of storm effects and that kind of thing, which is pretty cool. Other ones, Uncharted 4, a good one to look at in terms of when we look at games, in terms of water effects. Assassin's Creed Odyssey, kind of a more recent game, I would say, over the last few years that has been made. So they did a lot of work, Ubisoft did a lot of work in terms of making this part of their game, especially with their new Assassin's Creed Valhalla. That new one also has a lot of sailing and that kind of stuff, and you can see the same kind of water effects, or a little better than what they had before. We can't forget Sea of Thieves, because Sea of Thieves, like we just met, that was mentioned, Andrew mentioned Sea of Thieves as well. Really great water effects, foam on the water and those kind of things. And of course, I've been playing Valheim, and Valheim has its own water effects, and this is done in Unity. And you can see it not only has water effects, but it has all kinds of lovely stuff in terms of weather, crazy weather effects, and water and stuff, and all done with something that you guys could generate yourself. And then there's also Crisis, and Crisis might be one of the best examples of a couple of things here. So not just water effects in terms of the way the surface looks, but even underneath the surface. So that's water caustics. All right, so things that are in the surface as well as outside of the surface. And then we've come a long way, right, from where we were back in the day, right? So lots of improvements since then. So let's take a look at something that you can do locally for yourself and practice with Unity. So here I've kind of put together a little Unity project as an example. And you can see that I've got a little plane, and this is using just the plain old Unity assets. They're a little old now. They're from 2018. The standard asset package. Unity hasn't really updated that. I don't think they plan to anytime soon. But one thing it comes with is a really cool prefab that's with water effects. You can add water effects to your game pretty much in minutes, which is what I kind of did just before this class. So let's see what that looks like. And if I start going, there's also going to be a bit of sound. I got a first-person perspective kind of prefab that I'm running forward with. And you can see that I got this little water effect happening. And it's pretty complex. Like you see that there's reflections We've got a little bit of refractions. It's picking up a little bit of the sunlight, right? So the horizon and that kind of stuff. And it looks fairly realistic, although if you see, it's a little bit regular in terms of its wave properties. One thing that's bad is, well, if I go into the water, there's nothing. It's just really a water surface that really doesn't show any of the caustic effects. So water caustics is a totally different thing than actually the water surface. And then we're going to talk about those two things as separate topics. Okay, so again, how did I produce this? It's not that difficult to do in Unity, of course, and this is the same kind of engine that Valheim was created with, right? So again, if you look at the, all I did was have a kind of a prefab for water. Now this prefab for water has several different scripts attached to it. And notice that there are normals, a normal map for the texture, as well as shore and foam, which kind of adds that more realistic effect when it comes to that. You can change many different features on it. And so this is the kind of stuff that you want with your own shader, right? Even though this is Unity, it doesn't matter. The idea is the same that we have here. So you can see that there is specular highlights, reflections, and also displacements. And you can change any of these features. So for example, I can, look at the steepness on the across the x-axis, or I can increase that across the y-axis. Let's make that something like insane, like 20, and see what happens on the y-axis. See how that changes my water. My speed, I can make it much faster. Let's say 20 times as fast as it was before. And let's see what the effect is going to be when I modify it this way, right? You can see that it's much faster. It doesn't look as realistic. It looks like I'm part of a pond or something, or maybe a bathtub, as opposed to something else. Great thing about Unity is you can modify these things in real time, right? So you can see the real-time effects of really slowing it down to something more realistic, right? And you can play with these things, so you can see the effect. So that's something that you want to play with. Again, it doesn't matter what you're looking at, whether it's Unity or whether it's something that's more, that's something that you break on your own with OpenGL. At the end of the day, the idea is the same. So we're going to get into how this is done a little bit in a second. All right, so again, water effects. So how do we do it? All right, really what we have is we want to be able to start thinking about using some kind of shader to animate a surface. And we're going to use a time-dependent function a lot of times in order for us to do that. All right, so we're going to take a surface, we're going to displace the surface in some way, right? So change the way that it looks. Now we can do it by actually creating a texture, or we can actually take an existing texture and modify it by using a displacement map, okay? And some kind of scrolling, we can actually have some kind of scrolling shader. There's lots of ways to do this kind of stuff. And the things that we're going to mention here in the PowerPoint is just a few ways. So again, we're going to be able to take some kind of quad as an example. And what we're going to do is we're going to modify the surface across the XZ plane. And we're going to modify the Y coordinate with some kind of time-dependent displacement function that's going to change how this looks. A lot of times we use some kind of noise as an example. Noise is a popular way of creating a randomized kind of effect. Sometimes we use a Perlin noise or other kind of noise effect to create kind of ripples and those kind of things as we procedurally generate the effect. Okay, so that's kind of something we use. Most of the time we use some kind of sine wave or some kind of, again, time-dependent function that changes the displacement of your y-axis across the surface of the texture, and that's what you want to do. And you want to do it in some kind of rolling fashion, so it doesn't change it randomly and everywhere. It's going to look weird. It's got to be kind of something that moves, as well as a slow move across the x-axis or the xz plane, as well as some kind of wave across the y plane, right? And again, this is assuming that y is up in your reference frame. So again, we could think about modifying the the normal vector and how that's done. But first, of course, what we want to do is we want to normalize everything to 0, 1. How would this look? it would look something like this, where we kind of create a fragment shader that computes, the fragment color based on position and normal, as an example. And once we have that, and again, this is just for reference, I'm not going to look at the code right now, but really what it looks like is we look at the position of the vertex, and what we want to do is we want to update the y coordinates using some kind of wave equation. And again, we want to do it across some kind of time-dependent function, sine function or something else like that. What we're going to do then is we're going to have this vertex position variable, and we're going to use that to modify the y coordinate, and we're going to compute the normal vector using, again, that equation that we looked at before. And that, the previous equation right here is where we're going to take the position over time, and we're going to modify it. That's what we're doing here. So again, really, because the wave is two-dimensional, right? It doesn't really depend on the z-axis in any way. We're really thinking about the z component as 0. Okay, so we don't care about that too much, right? So that's kind of the idea behind what we do. So that is the wave. So the wave, that's kind of the surface. So the first thing we do is we modify the surface so that it actually, kind of produces the effect that we want, which is that wavy effect. And you can try different things to accomplish that. Again, we're going to modify the vertices with the time-dependent function. But what about water caustics, and why are they called caustics? So think about, when you think about water, and if I close my eyes for a second and I think about, how water feels when I'm underwater, my eyes there's a bit of blurring. That's one thing that we're going to see. So we can add a blur effect. So that could be a post-process effect when you enter the water, and it can be position related. So as I enter the water, I turn on a post-process effect as an example that makes it look like it's blurry right away when I'm inside the water area. Okay, so that's the first thing. And the second thing is, because my eyes aren't going to see underneath the water as clearly, the other thing that I can add in there is you're going to have a refraction of light as it passes through. So you got to think about how that works. It kind of looks like this. How does it get to this? So what really happens is light rays are both reflected off the surface of the water in real life, as well as refracted as they pass through the water. Again, think about water as a refracting medium, something that's going to change the way the light. It's going to change the path of the photons as they pass through the surface of the water. Right? It changes the path. So it looks like as if, if you put a stick in water, it looks like it's kind of bent. And the reason why that happens is because of the way that light passes through water. Light passes through air in a different way. And as humans, we can perceive, we have a different perception in air than we do in water. If we had some kind of, as an example, a nictating membrane that came over our eyes, so when we went into water, all of a sudden we didn't need goggles, and we can see underneath the water as well as we can kind of on the surface. But even so, even if we do, when we're in a pool and we have goggles on, we still see this refraction effect that happens, or this bending of light, this glittering that happens underneath the surface of the water. And sometimes it even looks like God rays. If you kind of like, kind of deep inside, let's say some kind of deep pool or ocean or something like that, right? Because again, the water is the light is passing through the surface of the water, and that it's dispersing. Okay, so that's the effect. So again, that's exactly what's happening. We're seeing, again, we might see a fish that's over here, and as an example, but really what's happening, the eye is actually seeing the fish in the wrong position, and what we want to try and do is aim for a different position. This is the real position, but this is what it looks like to us. Actually, it would probably be more like this. This is probably where how it appears to us, but really it's over here. So that's why when we have to, the difference between air and water, it gets kind of this idea of refraction, and photons get reflected and refracted according to Snell's law. All right, where we have the index of refraction, and depending on the index of refraction of the liquid that it's passing through, or the medium, then we're going to get a change in the ratio of what we see compared to, and that's what this is. They've got different proportions according to what we perceive in air in one medium compared to what we perceive in water, a second medium. Okay, so that's what's happening. So one of the things we're going to see when we're looking into water is from the air is some kind of refraction. Okay, if we want to make it more realistic. The second thing is we're going to get a lot of reflections. So reflection off of the water. So if there's something on top of the water, and again, if you looked at my Unity scene, you saw that there was light that came from the horizon. You're going to get reflections, and you're going to get the particles or the pixels that are in on the light on the water surface changing, right, to to mimic what it's like, again, with this kind of scene. We're kind of like reflecting the whatever the scenery is above. How do you do that? That's kind of the thing that we want to do. Remember that video games, and especially CG, is all tricks. A lot of it is math, but some of it is, we got to think about how do we mimic the thing that we see in real life. It's not going to be quite as good as real life, but it might be, for us and for our video games, good enough. The more realistic we're going to get when it comes to, computer graphics effects, the more of an impact it may have from a performance perspective. So we have to kind of find that happy medium between performance, as an example, and realism. Okay, so it might look cool. It might look good enough where it's okay for your game. Okay, and that's where I think we have to relate it back to. So again, caustics are kind of new when it comes to the way it works. It's a lot of times when the first original research back in '96, and that's why we say it's kind of new, because it hasn't been something that's been studied for a lot of years. Just back then, they used something called backward Monte Carlo ray tracking to achieve this kind of caustics effect back in the day. That's how we kind of learned to do it now, right? But back before that, it was using additive blending, which is, was much different. This is how it used to look, and this is kind of maybe where we're going now, where we kind of have a different kind of effect. Even the Unity shader that I showed you uses some kind of Monte Carlo kind of randomized ray tracking. So other approaches, how do we do it? We can use bump mapping to simulate the perturbation of the water surface. So again, that we're looking at just the water surface now again. So we're bumping the plane, so it kind of looks like, again, over some kind of time-dependent function where there's some part of the area of the water that's being moved. Okay, that's what it looks like. Again, it's an illusion, but it can be done in several steps. So we can start thinking about also not just the motion. Motion is one thing, the surface of the water movement and how it looks, but the next pass is going to be the reflection. So there's a reflection render pass. How do we do reflection? We'll have two cameras, right? One camera that is above the water and a mirrored camera that is sitting underneath the water. And what we're going to do is we're going to render what the mirrored camera sees on the water surface, right? And so what this is happening is we're going to get a flipped view of what the mirrored camera would see outside the water, right? And at the beginning, it's going to look perfect, right? Something that looks like this. And then what we can do is we can take that image, and again, we can apply the distortion that we need of the water to make it look like it's, something that's been modified. Otherwise, this would look too unrealistic if you saw something like this, right? So again, we get the reflection. It's stored as a texture. And then what happens is we use only this, what it says, permutated reflection, to apply to the texture. So that's what we do. We kind of convert the clean reflection to something that's more perturbed, right? According to the motion, we want to match it with the motion of the water that we see on the plane. So the first thing is, let's get that motion going on the surface of the water. Then there's the refraction render pass. And so this is where we bend the water. So it's not just reflected, but it's actually moved and modified. So we see what it's going to look like inside. So again, so this is just the permuted reflection from last slide. And then this in here is the reflection in some kind of constant mix with the watercolor. So we're kind of matching the watercolor that's in there. And then what we're going to use alpha blending, right? So that we blend it together. And so we get that final effect. Now you can see that this is very similar to what it looks here, with a little bit more refraction inside the water, the things that are inside the water that we can see through it. So it's kind of neat. All right. So that's the refraction render pass. Taking it further, After that, once we've got that passed, the refraction is stored itself as a texture, and then it's blended back in with the original texture underneath, with and without fogging, to create, this is what would be inside the water, to create the final effect, right? So we have, again, the stuff that's in the water, the surface of the water, and we're combining everything together to get the final full water effect, the reflection, again, of the object, the refraction of the water surface, the stuff that's inside of the water, and again, it's all layered together in a post-processing effect. One thing to note is that this might be really hard to pull off with deferred rendering, right? Now, you guys have been talking about or using deferred rendering, and we talked about one of the challenges with deferred rendering is transparency, right? So again, it can be done, but we have to think about this idea of alpha blending. It could be done with layers. We can use, some kind of skinning, right? So, those kind of things, that the same effects we talked about before. So we want to do some kind of depth skinning or that kind of thing. Depth peeling is what it's called. So any of those kind of things can help us with this kind of effect, but you can see that sometimes using a forward renderer might be better. Now, if we had many lights in addition to the water effect, it can be a very challenging scene to produce. And that's why when we have video games, modern video games, especially when it comes to you looking at a water scene, they've done a lot of refactoring to that scene, depending on the platform that you're on. If you're looking at a particular game or, kind of through the lens of a modern game, and it looks good according to any platform that you're on, if you can compare platforms, you might see that there's been some changes made between platforms depending on the hardware, right? So example might be on a PC with everything turned on to full with some kind of ray tracing card, discrete graphics card, you might see some great effects. But if you put it on an old PlayStation 4 or an Xbox One or something like that, or even on a Switch, and you're looking at water, you may have a different kind of effect. It might look completely different because of the hardware, right, that has to deal with it. So here's a shader toy example. Let's take a look at this one. And one of the things I've asked you for in-class exercise 5 is, let me see if I can successfully pull this thing in here. And I'll turn off, actually, you should be able to see this now. In-class exercise 5 is take a shader, for either a water shader that you find with Shader Toy or a particle effect. We're going to talk about particle effects as well, and modify some of these values. Now, you notice, we have some control here, but you can see what it looks like. There are the same features that we're looking at. Now, we're not seeing caustics. Okay, that's not something we're seeing here. We're seeing water surface effects. Okay, that's what we're seeing here. And one of the things we're also getting is, and again, it really depends on if you like this. There's a little bit of, and it's amazing that they can do this on Shader Toy, by the way. But if you look at when the dolphin breaks the surface, the kind of effect that we see almost like a particle type effect around to create the splashes and the perturbations of the water in that particular area as the dolphin leaves and enters the water again. So kind of an interesting effect. We also see, a little bit of refraction, right? So the dolphin underneath the surface, and then what happens when the dolphin leaves the, kind of the water and comes out. So take a look at this shader. It's kind of interesting the way they did it. It's fairly well documented, I think, when you look through. So I think even some of the names of the variables and all that stuff, I think it's fairly understandable. And they also have different channels to accomplish this, kind of effect. So take a look and see how they've done it. There's also another example that I want you guys to look at that's online, again, of water effects. And this is more of WebGL. So this is kind of interesting. They can do this on the web. So we have, again, some kind of surface, right? As an example, I can rotate it by pressing my middle mouse button, right, and holding it down. I can grab the object. You can clearly see the idea of what we're seeing on the surface compared to what we're seeing underneath the surface. Now you can see that there's clearly no caustics. If we're in the surface and I'm moving the object, as an example, we don't see water caustics, but we can see disturbances if you pass your mouse across the water. How do they do that, right? And it talks about how to interact with that, how to turn it off and on. The effect can be toggled, all right, as an example. I can change the directional light, right? So we can turn the directional light on. So whatever we want in terms of the direction, right? There we go. So I can change the direction of the light. And once the light is changed, then the effect of the water, we see a bunch of stuff happening, right? It looks like we're seeing as the light passes through, what happens at the bottom of the pool, this effect now. And we also see the effects here of the surface as the light passes through. So it's almost like it's passing through this texture, and it's being, some part of the light is being occluded by the texture to produce the effects that are inside the water. So not quite water caustics. We don't get everything, but it's not terrible either. All right, so it's pretty good. Again, that's a WebGL effect. So really cool. Take a look at this. It says for details, there's some great, kind of view on how this works. So that is a WebGL example. All right, so questions about water and how it's done, how it's used. So again, let's go over it again before we leave this section. So the first part is we have to kind of displace the surface somehow, right? And we're displacing the surface with a time-dependent sine wave or some kind of wave, and we're displacing only some part of the surface, but not the other parts. So imagine if I'm taking some kind of waveform and uniformly across some kind of tessellated quad, I'm taking it and I'm warping it, as an example, with a shader effect. That's what I'm doing, okay? And I'm warping it over time. So really, I'm just moving it up and down. Then I'm moving it, the effect is I can scroll the effect. So I can kind of, make it so that it scrolls outward. If I make it scroll outward in all directions, it produces a ripple. If I make it scroll in one direction, let's say across the x-axis or across the z-axis, then it looks like there's a wave. Okay, so that's how it can be done. And then the second thing is, what about reflections? We use a second mirror to create a secondary texture. It's a mirrored camera, a mirrored camera that kind of sits underneath the water plane, right, and looks up at kind of similarly to what is being seen, and we take whatever's being seen by that mirrored camera and we reflect it, or we kind of add it to the surface of the water to produce that reflected effect. And then what we do is we do another pass where we do refraction. And what we do with refraction is we take we modify the way the objects look inside the water, right? By perturbing or, changing the way that the reflection is being seen. We perturb the reflection. And we refract the water, so the things that we see inside the water are slightly shifted compared to the things that are seen on top of the water. So again, on top of the water, we're going to shift what the camera sees when it passes through the water plane, and we're going to add that to the texture additively through alpha blending to the texture of the water. It's the water itself, and this is on top of all the waving and everything else that's happening, and that's how we can produce the effect. All right. What about particles? And particles, I mean, I think Dr. Hogue has talked about particles, and you did a whole thing on CPU particles in your animation algorithms class. And that was a good thing. That was using, kind of creating particles on the CPU. And one of the things we always saw was that, juice it or lose it video. I remember seeing that when I first was at Ontario Tech, and it's from several years back at GDC. And it talked about how, when we add particles and screen shake to a scene and to a game, it's that much more awesome. Okay, so that's something that we want to see. Just going to take the optimize for video off here for a second. So again, I think one of the things that we wanted to try and do is add particles to our games. But the challenge is, the more particles we add, especially if it's realistic particles like this, we're going to see that the impact on the CPU for so many particles, and this could be a scene with, let's say, 3,000 particles or more, right? If we do it on the CPU side, plus everything else that's going on, AI, we're moving, we have some kind of AI brain in every one of our enemies, pathfinding, we have our character controller, the way we've created it, the camera, lighting, post-processing effects. Everything is happening every frame, my friends. So when we have all that going on your poor CPU, it can be quite a load, and it can really kill your performance, particles. So a lot of times what we want to think about is what really happens with particles and what the most important effects are. Again, think about a particle. It's born. It has some kind of animated effect by some kind of rules. We might change its color. It might, change. It's obviously going to change its position over time. It's going to probably change its transparency over time. Its size might change over time. All these things for every single particle in the emitter. And we might have several emitters to create an effect. All right, so this is the kind of thing. And then finally, each particle dies, right? So it lives and it dies. Or if we're smart, what we might want to do instead of making particles live and die, which means instantiating and destroying, is might be something like we might have a particle pool. And that's just something we can think about. An object pool that we reuse the particles. We just turn them off instead of getting rid of them, because what that can cause, and we're going to learn about this in game engines, is, Jonathan, it was Samantha for you, Dr. Hogue for me. But what it might cause is something called memory fragmentation, right? So memory fragmentation happens when you instantiate and destroy stuff. Because when I instantiate stuff, I allocate memory. And usually it happens, let's suppose, on the heap, right? We don't do it on a stack, that's for sure. And then as we allocate memory on the heap and we destroy stuff, we have these little holes that appear in the heap. Unless we optimize how we use our memory, then what ends up happening is we take up more and more memory as the effect goes on. All right, so that is kind of an overview of particles. And let's think about some basic rules. We're going to use some basic kinematics, and we've seen the same things. You've already learned about these in your animation algorithm. We're also going to use some other effects. Maybe we're going to have a wind effect or some kind of friction, whether it's surface friction on on the ground, or if you're going to make a spark-like effect where particles kind of speed up or slow down, those kind of things. Some kind of acceleration due to gravity or other accelerations. Again, we talk about these things, changing shapes, colors over time, even transparency. And now we got to think about this again. Remember, once I talk transparency, in your brains, you should think about, wait, what about deferred rendering? Because that transparency and particles in deferred rendering now we're talking about. So there's like thousands of particles on the screen potentially, and we got to think about deferred rendering. How do we pull that off, right? Again, not impossible, but there's some tricks that we can pull off. So again, let's say, for example, I want an effect like this. What do I do? And I want this effect to be on the GPU side, not on the CPU side. Again, what we want to think about is this idea of kinematics, which you guys have learned about in animation algorithms. And we're going to take our basic kinematic formula, which is P naught plus V naught T plus 1/2 AT squared. This idea of a position of a particle over time, it doesn't matter. This applies to so many things. This equation is like, it's the God equation when it comes to physics, if you think about it, right? It's like I can take a particle, or I can take an object, a spaceship, whatever it is, and I can add the acceleration and velocity over time and create almost like, a very realistic movement by deriving other equations from this equation. Again, P naught is the original position plus the original velocity times time plus your 1/2 AT squared, and that'll be your new position at time t. Okay, that's how it would work. All right, so that is your kinematic equation. You should have learned about this as well from your math for games 2. Again, I'm not sure if you had Dr. Hogue for that one or not, but I'm sure that they talked about some kind of kinematic equations in your physics class during that time. So we're going to apply the same kinematic equations to each of the particles, and that's just as a review is what you would have done in your animations algorithm class. So how do we do it in code? Well, again, we're going to store the initial velocity for each particle somewhere. We're going to randomize the values for a range of possible vectors. Again, what we want to think about is creating a vertical cone of particles, if we're going to make that the effect that I showed you, right? From a set of vectors. And a lot of times, if we want to make our cone, we want to use spherical coordinates as opposed to rectangular coordinate frame, all right? Where we use things like, theta and phi to define an angle and a possible direction. All right, so that's the kind of way we would do that. So spherical coordinate system. And then what we want to do is we want to use a second buffer to store the start time for each particle. And we want to create an array of floats. Again, this is all on the, we want to do this on the GPU. We're going to kind of create an array of floats. And what's going to happen is you want again, a particle texture. Sorry, I'm just getting a little bit of a question that's coming up too. Nope. That's the answer to that one. Nope. As well as, I'm sorry, I'm trying to monitor Discord, guys, YouTube, and what we have in class all together at once, and it's kind of very challenging. So bear with me as I'm trying to answer the questions that I'm getting. I'm glad there are questions. Sometimes people are very quite silent, and it's, you know, there's not any questions, and I think that can make for a very challenging class. So yeah, so I think that's the so that's the kind of stuff that we let's go back. Sorry, I lost my track here. So the second buffer has the time for each particle. We create an array of floats that start at 0 and increment by the rate, whatever the rate is, and that's going to give us the emission rate, and that's what we're talking about before. Okay. So again, some things that we want to keep track of is we want to set the following uniform variables from within the OpenGL program: your particle text, which is the particle's texture; time, the amount of time that has elapsed since the animation began; gravity, your particle lifetime, and other stuff. Okay. Don't forget about particle size. Okay, something that we want to also keep track of as well. And this is what your vertex shader might look like, where you have your uniforms, your time, your gravity, your particle lifetime. And then what you're going to do is you're going to modify each particle according to those values. It's going to pass into the fragment shader. Fragment shader is quite easy. We're just going to apply the transparency, as well as we're going to sample from the particle texture, and it's going to produce each of the particles. So that's the particle itself on the GPU. So a couple ways to create particle systems. Again, one of them is to use something called transformed feedback, and the other one is to create instance particles. All right, so transformed feedback, again, is something that we would use the transform, and we'll talk about that in a second. And instance particles are GPU instancing, so we create them on the GPU side altogether with the geometry shader. Okay, let's take a look here. So again, so here's a way of doing it. We're going to, the first way is using transform feedback, right? So a way to capture the output of the vertex or the geometry shader to a buffer for use in subsequent passes. So we're going to kind of pass it in. And then what it does is with particles is it enables to use discrete simulations for each of the particles, right? And then the particle position, and what we're going to do with it is we're going to be updating it within the vertex shader first. Okay, so again, everything that happens to each vertex, it makes sense to happen in the vertex shader. Any motion, transformations, movement, all that vertex side, and anything color-wise or those kind of things we can mostly do on the fragment side. Although, to be honest, you can do it on either side, right? I've seen it done on both sides, both on the vertex side and on the fragment side. It really depends on the effect that you want as it passes through the pipeline. All right, so we update the particle's position on the vertex shader, and then render that updated position in a subsequent pass or in the same pass if you really want to do that. And then what you do is you take those updated positions and you use them as an input to the next frame of animation. So every single frame, you're going to take that same thing and you're going to pass it back into the vertex shader again and again as you move the particle from one position to the next. So that's how you'll be doing that. And so this again is this idea of transform feedback. You're taking the transform of the particle, so that's position, rotation, and scale, and then you're passing it back into the vertex shader over and over again. Okay. So what are the differences from the previous approach? Instead of using an equation that describes the particle's motion over time, right, the particle positions will be updated incrementally. So that's what happens with the transform feedback approach, right? So you pass it in. Once you modify the particle, you pass it back in, and it provides this positive feedback loop. Okay. And again, we have some information here. So example would be the position and the velocity here, n+1, right? Which basically what it does is frame n+1, so and modifying the previous frame n. Okay, so that's the position and velocity functions. And then we use the time step, right, or the animation frame in order for us to modify, that's what this part is here, to modify the particle's position over time. We can break that down further in that we might have the variable h, which represents the time step size. All right, so we can modify as a scalar, if you will, right? Or the amount of time that is elapsed between frames. So you can modify this as well. And sometimes we need to modify this because we want to adjust the speed, as an example, of the particle in our scene relative to other things that are in our scene as well. Okay. And here's the time step or animation frame over here. P particle, whereas the P and V is the position and velocity, respectively. So again, how does this work? We use 2 sets of vertex buffers and swap their uses every frame. So again, buffer A, it provides position and velocities as input to the vertex shader. And then the vertex shader updates the position and velocity using some kind of Euler method, right? And sends the results back to buffer B using the transform feedback method we just talked about. And then in the second pass, or in the same pass, really depending on how you want to do that, we render the particles using buffer B, okay? Once we have the buffer, we have everything in buffer B, we pass everything to the fragment shader. Okay, so that's kind of how it's done. So that's transform feedback. And let's talk about it step by step. So we send the particle positions to the vertex shader. We do those transformations. We swap buffers from buffer A to buffer B, and then we render the particles at their updated positions using buffer B in the vertex shader, swap the buffers, and we have everything out into the fragment shader, and from there into the FBO. Okay, so how about if we want to create something with instance particles instead? So how do we do that? So it's called instance rendering, and it's another way of drawing several copies of a particular object with your geometry shader. Okay, and what you want to try and do is you're going to make a single instance of a particle. Maybe it's going to have speed or whatever, all the properties that it's going to have, and you're going to basically make a number of instances that are very similar. But what you might want to do is displace each of the particles in some way, the new particles that you've created, right, to offset their positions. As an example, let's say within that cone that you want to create. Okay, so that's the second way of doing it, using instance rendering. One thing I'd like to talk about, and if I had more time today, I'm going to cut this discussion short today compared to normal, because I want to talk about a couple of things administratively for you guys as well. So this lecture is going to be a little shorter than normal. Is don't forget a couple things. There's a lot of them, a lot of particles all the time. They move a lot. They appear and die, and they're also semi-transparent. And this for me is always the biggest challenge. And depending on the way you've created your pipeline and the kind of game that you want to make. Imagine combining something like this with hundreds of lights. How do you do that, right? And then now we're talking about a whole other thing you got to figure out, another problem to solve, right? So again, you got to think about what this means and what kind of scene you're going to try and set, and the colors and everything else. A lot of times we can pull off, the almost like the color of a scene. And you can do that by using your post-processing effect instead of actually using lights. So almost like an overlay on top of the scene that's also moving. There's also some other things that you can do, as opposed to trying to use particles. And each particle is affected, as an example, by many, many lights. You don't want that to happen. It can really increase your complexity, the complexity of your scene. All right, so that's really particles and water effects in a nutshell. Let's talk about your in-class exercise 5. So this in-class exercise 5 is worth 2.5% like all the other ones are. For this one, I kind of elected not to go the blog route, and I think it might be easier for you guys, maybe interesting as well, to do something with Shader Toy this time around. So what I'm asking you to do is take a look at a water effect and or a particle effect on Shader Toy that you like. So let's take a look at if we can find something on Shader Toy. I found a couple of them. Here is sparks drifting, right? So you can see that that works, right? And all I did here was I searched for particles, right? So here we have procedural fire, particles, and sparks, right? And I also looked for a seascape, right? So some kind of seascape right on Shader Toy. So take a look at a couple of different ones that you might like. Take a look at the values and see if you can modify the values that have been included here in your shader, and see if you can create your own effect. The alternative to this is, because now we're kind of entering the last part of semester, and you've had a little bit of experience now, some of you, and especially if you're someone who loves computer graphics and that's where you see yourself, then think about trying to make your own shader for this one. Okay, so again, if it's too difficult or if you don't have time, and that's one of the biggest problems with at the end of semester we run out of time, is you may not have a chance to make your own shader, right? So again, making your own shader on Shader Toy is what I'm talking about, right? So for water, if you're going to choose water, maybe you want to change the height, the displacement, the speed, the refraction, different kinds of effects that you want. Maybe even swap out things like the textures, the bump maps, anything else that you want. And you may need to also, do some work with Photoshop, especially when it comes to bump mapping and that kind of stuff, to change the way the water is going to look. For particles, you might want to change the lifetime, the velocity, the color, and those kind of things. And then experiment as much as you can, again, with the shaders. What I'm looking for, again, is very simple. I'm looking for a screenshot of the original effect and one or more screenshots of your version and the things that you've changed. I'm looking for at least 2 properties that you've changed that make a difference. I'm not looking for just like, okay, let's just change a value. If I don't see a difference between the original version and the version that you're creating, then it's like the same thing, right? So please make sure that there is a difference in the output. Okay, so that is in class exercise 5. Again, I'm making it due Sunday to give you just a couple of extra days. Normally it's due Fridays to get it done. Any questions around in class exercise 5 from anybody here or online? Okay. I want to move into kind of a more administrative talk for the last part of our lecture today. And this is where we're sitting. Okay. So again, there's been questions asked about the exam, the final exam. Again, just to reiterate, I'll give you more details about it next week. But the final exam is again broken out into 2 parts. The first part of the final exam is going to be a written part, similar to the blogs that I've given you practice on ICE 3 and ICE 4. So ICE 3 and 4 are an example of a question you might get, right? So take a scene, give me some analysis when it comes to this particular type of effect that you're seeing. What's happening in the scene? Explain it in terms of whatever I'm asking. Okay, so I mean, I know it sounds nebulous, but that's what I'm really going to go. I'm going to go for. There's also going to be some short questions I might ask, right? In addition to that, a few short questions on, see the stuff that we've talked about, shaders, shadow mapping, and those kind of things. They're not going to be trick questions, guys. I'm looking for you to actually look at the material that I've already given you, right? And anything that's not included in the package that I've uploaded to Canvas will not be included as an example in your final exam. So if I haven't uploaded a PowerPoint, or if I haven't done a video or something like that, it's okay. It's not going to be on your final exam. The only thing that's going to be on your final exam are the things that I've asked you about, the things that we've done in class, that you've done within your in-class exercises, or that you've practiced with your in your in-lab exercises with Nick, or anything that we've asked you to do in an assignment. Okay, so those are the things that are going to be our fair game on the written portion of your final exam. And again, I'll talk about that again in more detail next week. I'll give you some examples of some questions that you might see. Okay, and I'm going to use the terms eerily similar. because that's what I've always enjoyed when a professor says it's going to be eerily similar to this, and of course the students, they don't listen, and then when they come and face their exam, it's very similar to what I'm going to give you next week. So please make sure you attend next week, as it's going to most likely help you with the things that I'm asking for your final. Then there's going to be the other piece, which is going to be your your technical piece, your practical piece. And the practical thing that you're going to be doing is going to be basically something that we've done in one of your assignments, A1, A2, A3, A4. It's individual this time instead of something that is, a group. And I'm going to probably ask you to do something that we've talked about. Most likely, you're going to see a G buffer in there. There's going to be questions around you making a G buffer, doing deferred rendering, doing post-processing effects, something like that. Now you're going to say, wait a minute, Tom, how the heck am I going to do that in a 2-hour period? And remember what I said earlier, and some people have forgotten this, and they've asked me, so should I book time with the, with the testing center or whatever? No, you don't need to do that, all right? Because remember that our exam period is over a period of 2 weeks. Am I wrong? I think it is, right? So because we have the exam period, what's going to probably happen is I'm going to give you the both pieces of the exam that you'll have for, for example, the written will be the first week, like I said earlier, this semester, and then the practical will be the second week. You'll have the entire week to get it done. Now, that may not sound like a lot of time for you, but it'll be way better than the 2-hour period. Okay, so everyone will have the same time frame. I'm not, it's not, but I'm going to gear each piece. So, example, the written should be able to be done in an hour-ish. And the technical piece, you'll get a starter, some kind of starter code that you'll work with, and then you'll be able to do. You should be able to complete the written again within about a 2-ish hour time frame. And I say ish because some people want to take longer, some people will be able to finish it faster, but it's not something that's going to take all week. I'm not going to make it so that it's a mini assignment that's going to kill you and really stress you out. I don't want that to happen. So that way it's going to be based on something that is within the reasonable time frame. So guys, don't panic, I think is the message I want to give you before we finish early today. I'm going to give you back a bit of your time today. The idea behind this is that we're just evaluating you on the stuff that we've talked about in class. If I'm asking you to look at something, look at your PowerPoints, study from the stuff I've given you. I'm probably not going to ask you to look something up, in a scholarly journal. I'm probably not going to ask you to do that. I'm probably not going to ask you to do everything in an IEEE format, because up until now, I haven't asked for that. So, if you want to produce it that way, you can, but it's not about that. It's about taking a look at the stuff we've talked about this semester, and then can you answer the questions? Can you kind of talk intelligently in your written about maybe a scene that I've asked you about, or a video game effect that I'm getting you to analyze? And can you give me feedback, intelligent feedback, similar to what you've already given me in your in-class exercise 3 and 4. Now, one thing to note is that there are certain people in the class, for whatever reason, that did not complete their in-class exercise 4. Some people didn't complete 3. For those people doing this, you may want to go back and take a look at some of those in-class exercises. And those are great practice, because I'm going to ask you to do some of those, those exercises as well. Will there be math? That's another question I've got in my in emails and stuff. Will there be math on the exam? No, I'm not going to give you crazy math questions to answer on the exam, or interpret this formula. Did we do that in class? Did I give you to do that on an in-class exercise? Did you have that in an assignment? If I haven't given you an assignment or an in-class exercise, it's not fair for me to do that on a final exam, so you won't have complicated math on the exam. All right. Do I need you to memorize the shader code from scratch? No, you have references to, Nick's code, your assignment code. The only thing I'd ask you to do is please don't copy from each other's repos, right? It's got to be your own repository that you're using, if possible, right? Will you have to do a repository, version control and that kind of stuff? Absolutely. You're going to have to do version control. That was something else I got as a question. What about a video? Were you going to make a video? Absolutely. You're going to make a little video. I know people hate videos, but you're going to make a video that basically you're going to talk to your code, that kind of thing. And what about screenshots and that kind of stuff for your written? Yes, and you're going to have to cite your screenshots. So these are all the questions that I've gotten so far. But when we kind of get together next week, when we talk about exam review, I'll have dates for you, as well as, again, some samples. That's what I'm hoping that I'm going to have for you next week on Wednesday. All right, so please make sure you attend, and this way you can practice and that kind of stuff. Any questions around anything we've talked about today? We've talked about a little bit of water effects and particle effects on the GPU, as well as your administrative stuff, which is your final exam. Okay, guys, I'm not seeing any questions. Thank you so much for attending. I really appreciate it today, and I'll give you back some of your time. I'll see you guys next week, and good luck. Please don't forget to work on assignment 4. If you haven't started working on it, I recommend getting to it because it's a bigger assignment than assignment 3. Guys, take care. Thank you so much, and I'll see you next week.